So we've just seen that the accumulator now equals 88. There it is. After ANDing it with AA, and we can actually, we could actually you can prove that by doing the AND in binary. But also notice that the sign bit has been set, and that is by design. So the 6502, when you're doing any kind of computation, any kind of binary arithmetic, it says if what we've done there is we're testing bit 7. So we're saying if bit 7 is a 1, then we need to set, so that arithmetic order there says set the 8th bit, or 128 in decimal, else clear it. There we go. And notice that again, that's that not and. So set it or clear it, depending upon the test condition, the result of the test condition. And we do exactly the same for the 0 bit. If the 0 bit is if the result of the computation is 0, then we set the 0 flag, and if the result of the computation isn't, then we clear the 0 flag. And because the result of the computation was above 127 in decimal, then we set the sign bit, but obviously the 0 bit, the 0 bit isn't set because the result isn't 0. Now I'll come back to this just as a quick point. We know the result isn't negative. We know the result is a positive 88x. But the computer doesn't know that. The computer just says it could be negative because the sign bit, because the calculation has taken it above 127. We covered this briefly in a previous video, but it's worthwhile noting we don't have to use that as a positive number. We could use that as a negative number because this sign bit is set here, and we've said okay, later on we can use that for various tests and things like that, so branch on the negative flag and things like that. I'm not sure how best to describe that. There are quite a lot of YouTube videos out there to talking about this, but it's something to bear in mind, and I'll have a think about the best way of explaining. It's all about 2's complement binary arithmetic, and I may have to put a video together to just put some references to other YouTube channels. The other thing to do now is to show some testing. We can actually sort of go in and look at rebuilding the memory config file, just to sort of put in some other instructions, or we can just sort of use the one that's in there. And we can have a look at this one, for example, which is an indirect jump I put in at B100, and the indirect jump says go fetch the contents of B200, and B200 is FE, which is the low byte, and B201 as FC as the high byte. So if we execute that instruction there at B100, the program counter should end up equal in FC FE because of the indirect nature of the jump. We discussed that in a previous video regarding addressing modes. So if we do a go on B100, we can now see that the program counter is FC FE as predicted, and nothing else has changed, which again is predicted because the indirect jump doesn't actually make any changes to anything else. It just performs the jump, changes the program counter, and that's great. So what this has now proven is that in our instructions, the strange little instruction here for indirect. That works. The absolute addressing mode works. Did write some code to prove zero page and immediate as well, and they were proven as working. So phase 4 takes this one step further now and starts filling in the rest of the addressing modes and adding more and more instructions to do more and more things. In fact, phase 4 fills in quite a lot of the instructions and quite a lot of the other bits and pieces. We had all sorts of stuff into phase 4, but this is just as a general overview now of what we completing phase 3 to get us into a position whereby the CLI allows us to mimic a 6502 effectively on a breadboard or on a test bed somewhere that you can pass electrical signals into it and produce results. In our case, we pass code into it and produce results, but it's the same principle as it would be if you were doing this on a test bed or on a test bench with a real 6502.